all of the objects orbiting the planet right now operationally are modeled as cannonballs, as spheres.
Hmm.
And I have to tell you that not many of them are spherical, actually. And so the thing is, the physics are already flawed. They're imperfect. And you might say, okay, well, how valid is this kind of cannonball model? And I would say, well, if you look at the current catalog that the Department of Defense maintains, about 26,000 objects, it seems like it's valid for about that, because that's the assumption that they make, right? So then the question is, if we're saying, well, we believe there's like 500,000 things up there that could be hazardous, but we only track 1% of that. Part of the reason why we're not tracking more is because of the flawed physics, okay? Because you can't predict, when I say tracking, what I really mean is you can detect an object and you can uniquely identify it. So we need to, so we need to detect it. And whenever I detect it, I need to say, yeah, that's Joey. I detected this and it's Joey 1, 2, 3 or whatever, the inability to assign a first and last name to the objects pretty much means you can't track. And I would say our inability to develop a larger catalog in part is because of this, not being able to uniquely identify objects. So whenever things go into this collision, calculation, there's a couple of assumptions that, these things have, these relative speeds with respect to each other, and they have a time of closest approach, and that time of closest approach is known and is fairly certain, and that the uncertainty with regard to the relative position between things can be modeled as a Gaussian distribution, and that already is not perfect. And so, interestingly enough, and it's all couched under a probability, and within the realm of uncertainty quantification, typically uncertainty quantification breaks uncertainty into two different kind of groups: uncertainty that's driven by randomness, and then uncertainty that's driven by systematic effects. And the random part is called aleatory uncertainty, and it's also called irreducible uncertainty. So the thing is, you can't really know something better than its inherent randomness. If something is truly random, you can't really know it more than that because it's random. If it's truly random, but then this other part of the uncertainty, this systematic uncertainty, is called epistemic uncertainty, and that is reducible. That is basically, think of it as the reason you don't know it is because you're ignorant. And so by bringing different sensors and observations, how can you remove the ignorance so that in an ideal world, you end up with nothing but the inherent randomness? Like, that's your goal, is to reduce everything to its inherent randomness. And because we assume that all the uncertainty in collisions is random, if you actually scale the uncertainty and make it larger and larger and larger and larger, eventually the collision probability goes to zero. As the uncertainty becomes really, really large, the collision probability goes to zero. And then I ask people, does that make sense to anybody, that the more ignorant you are of the collision, that the less risky it is? Of course not. But that's part of the math, because it's assumed to be purely random, and it's not. In fact, a lot of these collisions or near misses, let's say conjunctions, have periodic effects. We put things in specific highways. The highways have intersections. We know about these intersections. So sometimes these conjunctions between any two objects, it's like, yeah, every 3 days these things conjunct just because of the relative geometries with each other. But so that's not random. That's actually systematic. And so I think just the math with which we represent the uncertainty and how we are modeling the physics, those flaws to me are the culprit of collision risks that are not properly quantified. And so I think the system generates a lot of so-called type 1 errors, which are false positives, which are telling people, oh, all the time you need to move out of the way because something bad's going to happen. And people become desensitized to, the sky is falling, Chicken Little kind of thing.
More engineers are not going to solve your problem. It's not a technical problem in that sense. It's a process problem. And the time to fix your processes was 20 months ago, and the second best time is today. This is Jason Kanigan, the president of Cold Star Technologies and the host of this podcast, the Cold Star Project, which is all about identifying and solving process problems for space companies, because that's what we do. And you can hear the entirety of this episode by following the link in the comment below.